In this video, I'm going to show you how to convert raw data files for the titration labs that were initially recorded as drops into milliliters. When using the MeasureNet station, the equipment is set up by default to count the number of drops that are flowing through the drop counter. The station uses the user input of the initial and final volume readings from the burette along with the total number of drops to determine the average number of drops. So how do I know my students' data is in drops? Well, there's two different ways that you can determine that. The first is by going to the attendance page on Chem 21 and dropping down the download raw data option. You can look at the first set of numbers next to each file. If the values are whole numbers, like here with file 5, then the data is in drops. The decimal numbers, those that are less than 1, are in milliliters, like here with file 4. So in this case, file 5 and file 6 are the ones that are starting with 0, 1, 2, 3, 4, etc., and are the ones that are in drops. If you look at the student's graph in their assignment, you can also determine that the volume are in drops. So for instance, you have this student's trial 1 graph. First, remember the burette used in lab can only hold 25 milliliters of solution. Second, you also have to watch out that the excess labels are defined by default and not chosen to match the dataset. That is, the labels were programmed into Chem 21 and are separate of the data that was uploaded. So we have to ignore the axis label for the moment and look only at the numbers across the x-axis. In this graph, we see that the volumes run from 0 to 14, which makes sense because our burette maxes out at 25 milliliters. If we look at the student's next graph, we see that the numbers across the x-axis run from 0 to 180. That doesn't align with what our burette will hold at all. One of the most common questions TAs have is, why is my student's data in drops? The answer is both simple and complex. First, you have to understand how the station works. The drop counter is an LED sensor that blinks each time a drop is counted, which is great for a titration experiment. The average drop size is then used to convert the number of drops that were counted to volume. So that sounds easy enough. The problem is students must have the drops falling at a consistent size in order for the station to make the conversion. The drops must also fall at a consistent rate. Generally, if the time between drops is between 0.75 to 1.5 seconds, the conversion will occur. An ideal rate of 1 drop per 3 seconds will allow for the best mixed in the solution and the least amount of noise in the curve. Though for the most part, this is generally too slow for any of us to sit around and wait for. Then, when the calculation occurs, MeasureNet assumes a drop size of between 0.010 and 0.065 milliliters as the average. If the calculated value falls outside of that, then the station just assumes that there was an error in the initial or final volume being inputted and reverts everything back to drops. So these are the issues that must be resolved during lab with the student's technique at their station. If you don't resolve them, then we have to go back and we have to convert the data after lab. So how do we, post-lab, process the student's data from drops to milliliters? First, you'll want to log onto your Chem 21 account, find the assignment, and click on View Student Work. Then you'll want to select Attendance. On the attendance page, scroll down until you find the student's name. When you do, select Download Raw Data. Download the file that shows the volumes and whole numbers that is incorrect. In this case, we'll need to convert the data for file 5 and for file 6. The file will download as a CSV or Excel file that you can open on your computer or laptop using Excel. Prompt through the message to open the raw data file. Then open the drop to milliliter converter Excel file so that you can use both files at the same time. If you look at the student's data file on the left, you will see in column A whole numbers. That is indicative that the data is in drops. We will need to change the data file so that we get that into milliliters. We need to copy the student's data over to the converter file. Don't use Select All for this process. Instead, select the second row and all the way down to the bottom of the student's raw data and copy the data. Paste the data into the data converter file in cell B2. Once the data is pasted in, go back and look at row 1 in the student's data file and copy the values after const1 and constant2 into the data converter. These constants are the initial and final volumes entered in the station by the student. A quick check of the graph shows that generally the titration curve is smooth, but there is some outlier data that looks weird. So go to the bottom of the file converter to ensure that the data in columns B to F are all for this student. You will also want to check that the formula in column A goes all the way to the end of the student's data. Keep in mind that we frequently reuse this file, so there's often old data still shown. Your student may have collected more data on one trial than another, so we will have to make adjustments accordingly. In this case, we have extra data at the bottom, so we need to remove that old data by deleting those rows. Back at the top, we can see those extra data points are now gone off of our graph. You will then need to go back to the top and match the value in cell N7 to that of M7. This looks at the student's data and determines the last line, that is the total number of drops counted, and uses the value in the calculation of the average drop size. Those are the values in cell M2. Once the average drop size is determined, copy column A and paste the values only into column B, starting with cell 2. The values in column A are now the ones in milliliters. You then need to select columns B1 to K and the end of the data and copy the values to your computer's clipboard. Back on Chem 21, select Import Data. Paste the copied data into the large text box. Then update the file ID to match the data file you converted. In this case, we need to change the value to 5 and click Submit when you're done. Go back to the attendance page. Once you locate your student, you should now see your file with the updated data, as in it no longer has those whole numbers. Let's repeat the process for file number 6. The last step, we have to make sure that Chem 21 recognizes these changes and was able to determine the new equivalence points. So press Submit on the bottom of the attendance page to make sure the data files have updated. Then scroll down to Modify Graph Data. This is where we can manually determine the equivalence points. Find your student from the list. You should see a page that displays your student's graph data. Right under the graph is a series of inflection points and text boxes. These are the numbers Chem 21 is using as the equivalence points. Please notice that the Y value comes first and then the X. You will want to make sure that the current data to the right has a listed value. If not, we will need to add it in manually. When we get down to our updated file 5 and 6, we see that those do not have the inflection point set, and neither does file 4, so we need to do that. We can locate the equivalence point using the mouse coordinates displayed above the graph and enter those values in for the inflection point. Again, pay attention. The Y value for the inflection point is the top blank. You'll need to repeat this for files 5 and 6. Once finished, click Submit at the bottom. Chem 21 then displays a set of instructions that we need to follow. It says we need to go into the student's assignment and reset any calculations associated with these values, so to force the site to update the answers with the new values. So we go back to the lab menu and select View a Student Lab Sheet, locate our student, and scroll through their data sheet to see if the student has worked any calculated values past the graphs. If they have, we need to reset just those values.